stop here. The classification of matter by components. We know that looking to the diagram, the matter can be classified as pure substance or a mixture. So, and a pure substance can be an element or compound, while a mixture can be homogeneous or heterogeneous. So let's talk a little bit about this step by step. So when you talk about pure substance, it's a substance that is made up of only one component, and its composition is invariant, so no varies over there. So like over here, so I have my water. This is pure water, so I have only water molecules inside of my bottle, so that is a pure compound. Okay, so if I have a helium, a balloon full of helium, it's a pure element, so it's a pure substance. And since I don't have different atoms over there or different substance, I only have helium, so that it's a pure substance made by one element. So pure substance, as I said, an element can be a helium. It's an example. So cannot be chemically broken down into simpler substance. So a compound is a substance composed of two or more elements fixed, like water. For example, I have two hydrogen and one oxygen. So helium would be the element and water would be a compound. So only if you only have water, so that is a pure substance. So in the mixture, we can have homogeneous or heterogeneous mixture. So a heterogeneous mixture, a good example could be vinegar and olive oil over here. So we can see that it's no homogeneous mixture, right? So we can see the separation of those. I can see the oil spots over here in the liquid. So this is how you check a mixture. So it's depends how uniformly substances is within the mix. So when you look to the Gatorade over here, this beverage, it's a very homogeneous mixture because you don't see the difference. You cannot separate any substance over there visually, right? So that is homogeneous. So another example of homogeneous, your tea. So if you have a cup of tea, so you mix, it's a mixture of herbs and water, and sometimes a little bit of sugar, and you don't see the difference. It's a homogeneous liquid, so that is a homogeneous mixture. Okay, so let's see if you really understand the difference between a mixture, homogeneous or heterogeneous, or if it's a pure substance. Look at these images over here. A blue circle that represents an atom, and one type of atom, one type of element, and the square, red square over here represents an atom of second type of element. So which image is a pure substance? A, B, or C? Or you think that none of those are pure substance? Here you go. Yes, A, because A, imagine if this is a compound, okay? So imagine if you have a carbon monoxide over here, CO, and I only have carbon monoxide in all the circle here inside. So in this part, I have two different elements. So they are not compound, they are elements, separate elements over here. So if I have more than one over here, so that means we have a mixture. That is not a pure substance because I have different elements over here as well on this over here. And they're going to say, oh, but here I have two different elements. It's like water. So that is a compound. Water is a compound as well. But in my bottle, I only had water molecules, so that make pure substance, okay? Made by compound. So, and we can separate mixture, right? When you try to brew a coffee, for example, you mix your coffee beans or coffee powder and water, and then that goes through a filtration to separate so you can drink your coffee, right? That is a process of separation. And if you have a cup of water full of small particles, like a very fine, like sand, fine sand. So if you let the water bottle stand over there and over on a table, so you're gonna see after a while those particles will settle down, right? So you can separate by decantation. Okay, so there are a lot of different processes. For example, distillation. This is one of the processes that I use in my research. In my research, I produce bioethanol from waste. So one of the processes, the final process, is where I separate the ethanol from the whole sample. So they have different boiling point. So that was what make the distillation process viable. So here is the whole mixture. See, in the balloon over there. So I have the tower over here. So the one that with the substance with the lower boiling point is gonna go up early. So that will come out from this exit over here that goes through refrigeration step. Okay, so and here that is the cooling water over here. Okay, so here the vapor will be condensated, and then we can separate this substance over here. The other one that has a higher boiling point, when the gas start forming and touch the bottle here, the wall of the bottle, will condensate and come down because it has a lower boiling point. So that is one of the processes that you can use to separate through different boiling points. And the filtration was the first one that I told you. So like the coffee that you filtrate to get the liquid. So you drink the liquid without the powder, right? So, and also very important, besides understand all what is a mixture, what is pure substance, how we're going to separate some substance or solutions that we need to separate. So we need to know what is physical and chemical change. I'm pretty sure that you already know, but it's really good to go over a little bit. So physical change is the change that alters only the state or appearance of a substance, but not the composition. Or these are physical change. For example, if I have my water, that's liquid. If I freeze this, I'm gonna have solid, right? Ice. However, the properties are the same, so I still have water. So I didn't change the identity of my substance. However, when we change, for example, if iron passes through oxidation, so we have a rust, that is a chemical change happening over there because that is a reaction. Look at this. So I have the iron over here reacting with the oxygen in the air. So then we produce iron trioxide, that is the rust. So I'm producing a new substance. That is a chemical changing. So this is a chemical change because we change the composition. We have a new substance, like rusting. It's a chemical change. So, and understanding what is chemical and physical change, you need to know what is chemical and physical properties. So the difference between those. So physical property is a property that a substance display without change its composition. For example, the smell of gasoline will always be there, not because it's changing chemically, it's just because that is the scent of the gasoline. Okay, it's a physical property like odor, taste, color, appearance, melting point or boiling point, a density are all physical properties. Chemical properties will be flammability or can be corrosiveness, or acidity or toxicity. This is a chemical property because displays it's displayed only when there are a change in its composition. Okay, so the flammability, so that is will have a change over there, right? So that is a property that a substance displays only when the change happens in its composition, okay? Through, of course, a chemical reaction. Let's see if you got this. Look at this. This diagram here on the left represents a liquid water molecules in a bit. Which of these diagrams, A, B, or C, best represent the water molecules after they have been vaporized by boiling? Stop the video and try by yourself. You're right if you answer A. Of course, when you evaporate, that is a physical change. Remember when I said when I freeze, I will have ice, but it's still water, right? So here, when I evaporate, I still have water molecules. But here in B and C, see here in C, we have the atoms are separate, the elements are separate. And here I have molecules, but it's a molecule of hydrogen and oxygen. So they separate, and this will not happen a physical change, okay? So that is not happening when you vaporize the water. So we still have water molecules. Okay, so another important thing in chemistry and science in general is energy. Chemistry is about movement. Physics, everything is about movement. If your atoms, if your molecules stop, you die, right? Simple. So you're always in movement. And when you talk about movement, we talk about energy. Potential energy, kinetic energy, thermal energy. So what is the difference between potential and kinetic and thermal energy? First, we need to understand what energy means. So energy is the capacity to do a work. So, and the work is defined as the action of a force through a distance. So if I'm in the table and I'm pushing my bottle of water, so this I'm applying force. This is a work, okay? So when you push the box over here, it's applying a force. So you're moving the object. So, and then it's important to understand, so now that you remember, like it's a brush up for you, I know, that what is the energy and what is the work. So kinetic and potential. I always love to start with the potential. I don't know why they start with the kinetic, but the potential is the energy associated with the position or the composition of the substance. Remember, when I said that my research is about to produce bioethanol from waste. So what I'm looking for is the potential energy of my waste. The potential energy will be measured as the sugar content inside, because that is where is the sugar that I can use to produce the ethanol. And then the ethanol that I produce has a lot of energy inside. And I know that is the potential energy, but as soon as I start the process of combustion, I can generate energy. So that is kinetic energy, because I start moving my car, for example, if I burned my fuel. So kinetic energy is the energy associated with the movement, with the motion of the object. So, and the thermal energy is the energy associated with the temperature. So, in an object. So thermal energy is actually a type of kinetic energy because it involves movement of the particles. So here we have an example. So we have a building over here, and the 10 kilograms weight on the top of this building. So, and the roof of the building, and it has a high potential energy, which is unstable over here, very in the edge of this roof. And then this weight will fall, and the potential energy is converted in kinetic energy. So the dropped wave over here on the floor releases thermal energy when it heats the ground, and it has low potential energy. It's stable now. So summarizing, energy is always conserved in a physical or chemical change. It's not create or destroy. This is the law of conservation of energy. So when you eat, for example, your food will pass through a very important cycle, the Krebs cycle, that will break down the sugar through several acid-base reactions and will convert that in energy. And then you're going to use that energy to walk, to breathe, to talk, to think, to live. So this is how you convert that. Okay, so that is what you say, like I'm eating sugar and then I'm producing energy. So the energy inside of my sugar, I will release an energy that I wanna use to move. And of course, if I walk or run, I'm gonna sweat it, I'm gonna release some energy, right? So that is a conservation of energy. So its energy is always conserved in a physical or chemical change. Systems with high potential energy tend to change in a direction that lowers their potential energy, releasing energy into the surroundings. Let's see if you got this. Time for a quick understand check. What type of energy is chemical energy? Kinetic, thermal, potential. Think well. Potential energy. And you're going to ask me why. So why? Chemical energy is stored in the bonds. Okay, so let me just grab my pen over here. If I have, let me grab over here my pen. It's better to draw. Okay, if I have, let me see, that is a structure over here, right? That's butane. It's a gas, right? So 4 carbons, a lot of hydrogens, hydrocarbon over here. So the energy is stored inside in the bonds over here. So we have a lot of bonds over here, right? Between atoms and also in molecules, okay? Because it's stored and not based on motion or temperature, it's classified as potential energy. Remember when I said to you, potential energy is the energy stored in you. So the stored potential energy is released when you break down those bonds. Normally it's released in terms of energy, so heat. So chemical energy is energy stored in the bonds of atoms and the molecules. All forms of energy ultimately falls in 2 categories, kinetic and potential. And the chemical energy belongs to potential. Now you know why. So other very important thing here is the units of measurements. Very important. So we have the number and you have the units. In chemistry, in science in general, you cannot accept naked numbers. And it's really important. Let me see how I could show you the importance without talk about science. For example, if someone knock my door and say like, oh, I need money, and I say back, okay, so I can pay you 50 if you go back in my backyard and clean up everything over there. And after hours, the boy comes to me with a well done work and say, I finished. And then I hand to him 50 cents. Am I a bad person? No, I didn't never ever said that I would pay 50 cans or 50 cars or $50. No, he doesn't even ask me. And I didn't promise anything. See how important is a unit? If your boss tells you, I'm gonna pay you 1,000, and then you say, okay, good, I will work for you. And then you got there and you got 1,000 cents. And he says like, but I thought that it was $1,000. Could be, but it wasn't. So this is how important is the units. Okay? So in chemistry, units, standard quantity used to specify measurements are critical. The 2 most common unit systems are as follows. metric system used in most of the world, and the English system used in the United States. Scientists use the international system, which is based on the metric system, and the abbreviation SI as come from the French Système International de Unités. So the standard units that you're gonna see a lot in chemistry and all the science in general is meter for length, kilogram for mass, second for time, Kelvin for temperature. Those are the ones that you're gonna work a lot with me over here, and moles. That is the most common units that we're gonna use during this course. And those are the symbol. You can use a caps letter for meters. And a kilogram, a second, you don't use caps letter for second as well. Okay. Kelvin, you must use caps letter. Okay. And you don't use M for moles. You need to write down moles, because M, it's meter, or this caps letter M, this is a concentration, molarity. Okay, so the meter, we know that is a measure of length, and most important in a lot of problems, and also in your work that you're gonna find if you go to engineer, you need to convert units. So it's good to know that 1 meter is equal 1 divided by 10 millions of distance from the equator to the North Pole. So the International Board of Weights and Measures now defines it more precisely as the distance light travels through a vacuum in a certain period of time. So, but this is not so important over here right now. Most important is to know the international system and units that we're gonna use over here, like the mass, kilograms or grams, or the second as the time. So that is the unit that you're gonna use. We don't use hours, we don't use other units, we use second. Okay, and the Kelvin is the one that I use for measure temperature. So the temperature is a measure of the average amount of kinetic energy of the atoms or molecules that compose the matter. So temperature also determines the direction of thermal energy transfer, or what we commonly call heat. Thermal energy transfer from hot to cold, always. So Kelvin scale assigns 0 Kelvin or absolute 0 to the coolest temperature possible. So absolute 0, so we don't have negative values for Kelvin. That is the lowest temperature that we can get. And absolute 0 is negative 273.15 Celsius degree, or negative 459 Fahrenheit. This is the temperature at which molecular motion virtually stops. Lower temperature don't exist. There is no life at all. Okay, so you need to know how to convert temperature. So if I have Celsius and I add 273.15, I will convert this to Kelvin. Celsius, if you have Fahrenheit and I want to find Celsius, I need to reduce 32 from Fahrenheit and divide by 1.8, and then I will have Celsius. And it's important to know how to convert. We're going to practice this more, and we're going to talk about this, because if you know how to convert units, that is a huge step to know and practice how you're going to work in this stoichiometry. And you're going to say like, oh, this doesn't, how this, has to do with the stoichiometry. So because we work with the units. So when you learn how to work with the units, you will never more need to work with the formulas, memorization, or anything, because you know how to get there. So let's try and test your knowledge again. So here is which temperature scale has no negative temperature. And I just said that. Stop the video and try by yourself. Kelvin, Celsius, or Fahrenheit. As I said, Kelvin is the temperature scale that we don't have negative values. And that will be the temperature they're going to use and all the gas problems, for example, when you work with the gases. Okay? And one thing that helps a lot is the prefix. So the International System units use the prefix multipliers shown in the table that I'm going to show to you in order to better represent the numbers, like exa, mega, giga, kilograms, kilo, deci, centi. It's really important because you can work with large numbers or small numbers using prefixes without to write down all the zeros. Okay, the most important to know here is those that have over here: mega, kilo, deci, centi, milli, micro, nano, pico, femto, alto. No, it's the most important ones that I really ask you to practice and remember those. We use a lot of micrometers in biochemistry, a lot of microliters, because we use very small quantity of substance. So here we have this number here. Oh, looks small now because I use the formula to write down this. It's 5.57 times 10 to negative 5 meters. And asking which prefix multiply is most appropriate for reporting measurement of this number. And the answer is mega, milli, micro, or kilo. So kilo is only 10 to the third. So then we have a milli, and then you have micro, mega. What are you going to use? So the most affordable here, like, would be micro, because that is 10 to minus 6. So I could go on this 50.7 micrometers, and I know that is equal to this. Okay, so that is the most useful because this is positive, this is only negative 3, right? So we need to, I will just go back here just to show you. You need to look at this. See, like 10, negative 3, 10, negative 6, 10. So when you go to mega, it's 10, positive 6. So it's not negative. So here we have a negative, see? So it's better to use that, okay? So negative, and here we have positive, and here is negative 6. So that is the one that is most appropriate to use it. Okay, so you're gonna find another short video about how to convert units and everything, so that will help you. But this part is only to remind you that it's important to know the prefixes. Okay, very important is the derived units. Derived units is a combination of other units, like for example, volume is measure of space. It has units of length, cubit, like cubic meters, cubic centimeters, or liters. Density is the ratio of a substance mass to volume, grams per liter. It has units to mass divided by volume. That is derived units. Or density affects the substance will sink or float in another. The less dense substance that floats. So derived units, we have here the density. Look at the water density at 4 Celsius degree, close to 1 grams per cubic centimeters. If you go to 25 Celsius degrees, will be a little bit lower than 1, would be 0.99 something. So, but it's always be close to 1. So if you go to, if it tells you glass is 2.6, and I put a glass in a cup of water, you know that glass will sink, right? So the glass will be here. Why? Because the density is higher than the density of water. But if I get this charcoal over here and I put it in the water, this will float in the water because it's lower, the density is lower than the water, right? And if you like, because we're talking about units and because you're talking about density, it's important to know what is intensive and extensive properties. What is this? Is intensive property is a characteristic that is independent. That means no depend of the amount of the substance. For example, the density doesn't matter if you have a very small quantity of water or if you have a bottle full of water. The density will be the same. Doesn't matter if you have a liter or cup of 100 milliliters. So doesn't matter. The quantity will not affect my density. Extensive property, yes, depends on the amount of the substance, such as mass. So the mass of the water that I have, if I increase the quantity over here, I will increase the mass, right? So let's see if you got this. The density of copper decreases as temperature increases, and as does the density of most of its substance. Which change occurs in a sample of copper when it's warmed from room temperature to 95 Celsius degree? The sample becomes lighter, the sample becomes heavier, the sample expands, or the sample contracts. What do you think? Right, the sample expanded because you increase the temperature, and this is why the density will decrease. Okay, so as much of those substance. Okay, so the reliability of measurements, significant figures. Scientific measurements are reported so that every digit is certain except the last, which is estimated. So here you see the example. I have one number, 2, 3, 4. This last one is the estimated one. Significant figures deal with the writing numbers to reflect precision. The precision of the measurement depends on the instrument used to make the measurement. A ruler, for example, or any instrument that you can measure. The preservation of this precision during the calculation is accomplished by using significant figures. Let's count over here. The greater the number of significant figures, the greater the certainty of the measurement. To determine the number of significant figures in a number, follow these rules. Significant figures, all non-zero are significant. That means if I have here 1, 2, 3, for sure I know the non-zeros are significant. Interior zeros, that means zeros between two non-zeros, like we see over here. See, I have a zero between two non-zeros. They are significant. So in this example here, I have 3 significant figures. And then this over here, I have 1, 2, 3, 4, 5 significant figures. Okay? Let's see all those over here. So let's go on this example over here. Okay. So leading zeros. Leading zeros are the zeros to the left of the first non-zero digit. That means all those over here. They are not significant. That means we don't count those. See over here? Those are leading zeros. So we don't count those. So how many significant figures over here? So for sure I have 2, right? 5 and 4. But what about this? If you have a decimal point and you have a non-zeros over here, all the zeros after non-zeros will be significant. So I have 3 significant figures over here. So trailing zeros, that is the zeros at the end of the number. So trailing zeros of the decimal point are always significant, as I said before. Like over here, right? Like over here. However, trailing zeros before a decimal point and after a non-zero number are always significant. Okay? Trailing zeros before an implied decimal point are ambiguous and should be avoided by using scientific notation. Okay? Decimal points are placed after one or more trailing zeros if the zeros are to be considered significant. Okay? So here I have 4 significant figures because it's before the decimal point over here. Here I have 4, here I have 3, here I have 2, and here I only have 2 because these are not significant figures. I know that is ambiguous, right? However, it's you can use scientific notation like 1.2 times. Let me just use another pen over here because that is hard to use. So it would be 1.2 times 10. So we can 1, 2, 3, 3 over here. So we know that we have only 2 significant figures over here. This is the easiest way to avoid those ambiguous steps. So exact numbers like number of coins or numbers in a formula, they are not accountable. They are infinite. So we don't count significant figures. They are exact numbers. Okay, they are infinite numbers. So unlimited number of significant figures. So you don't count it. So we can say unlimited significant figures. Like if I talk about coins, I have 100 coins. So I don't have 100.85 coins. I have 100 coins. I cannot have 100.85. I have 111 people in the room. So I have one person in the room. I cannot have a half person over here, right? So it's a fixed number. So it's unlimited number. I can put like 20 people inside of my room or more. So it's unlimited. Okay, so we don't count significant figures over here. We can say unlimited significant figures. Okay. So it's important to know the difference between 2 types of calculations: division and multiplication, addition and subtraction. So why? Because they have different rules to count the final number of significant figures in our results, and this is very important because I'm gonna grade you on this in your assignments, exams, and also in your lab reports. And the multiplication and division, the results carry the same number of significant figures as the factor with the fewest significant figures. Look at this example over here. I have 4 significant figures over here. This is a multiplication, right? So for both. And I have here 1, 2, 3, 4, 5 significant figures and only 2 significant figures. So the least one is this over here, 2 significant figures. So my result will have only 2 significant figures. The same happens in the division. So the least number is here, 3 significant figures, because here I have 4, 5 significant figures, all right? So my number will have 3 significant figures, 1, 2, 3. So we stop over here. And pay attention on the how you count the significant figures. So the rules that we talked about. So we're gonna find another short, like another video, but it will be short. Just talk about significant figures, solving some problems. You're always gonna find some resources, okay? So if you don't feel good, still don't feel good on this part, please study, okay? Rules of calculation when you talk about subtraction and addition. So here you only gonna look to the number of decimal places. So in this case over here, look, I have a 3 decimal place, 2, no, and 4. So my result, my final result must have 2 decimal places. That's why I'm gonna stop here and 2 decimal place. In this case, I only have 1 decimal place, so I'm gonna stop over here, 1 decimal place. Okay, see how I rounded? So this is important. If the second number here is over 5 or equal 5, we increase 1 over here. This is why it's 5.7. In this case, I have 2, which is lower than 5. So we don't increase, so we keep it 41. Okay? This is the rules for rounding. So round down if the last or the leftmost digit dropped is 4 or less. Round up if the last up or leftmost digit drop is 5 or more. Exactly what we did before. Okay? And this case is greater than 5, so it's 5.4. Lower than 5, 5.3. Here is 5, so 5.4. And here, so if I have to increase, but this, look, it's 4, so it's 5.3. Now, in the last example, that only the last or leftmost digit being dropped. Determine in which direction you need to write. Ignore all digits to the right of it. Okay? So rounding multiple step, like to avoid rounding errors, you only round at the end. So your final answer. So you're gonna keep all. So see, I should have just 2, right? Digits, 2 decimals. So see that I mark it, I underline at least the least significant digits over here. So and then here I know that you're gonna have 2 significant digits, and here it's 4 significant digits, and here 3 significant digits. So I make my math with all the numbers, and then I know that my final answer must has only 2 significant digits. So then I'm gonna round, and I have 19. Okay? So you only round the final results. Very important science is precision and accuracy. Accuracy, it refers to how close the measured value is to the actual value. And the precision refers to how close a series of measurements are to one another, or how reproducible they are. Like here. So here, see, all my measurements are very far away from each other and also from the target. So I have low precision and low accuracy over here. Look at this. It's far from the target, so I have a low accuracy. But they are pretty close to each other, so I have a high precision. Here I have a low precision, but I have a high accuracy because they are all close to the center, the target. And here, all the samples are in the same area, so they are pretty close to each other, and they are pretty close to the target number. So it will be high precision and high accuracy. Let's work with the numbers because this is what you're going to do in class, right? So look at those results over here. Student A, student B, student C. We have 3 students over here. They repeatedly weighted a lead block known to have a true mass of 10.00 grams. So look at this. Each of the students have a different mass. If you analyze each one, can you tell me which one we have low accuracy or high accuracy, which one I have a high precision or low precision? Let's go to the first one. Look at this. I made a graphic. The graphic is easier to understand. So here is not close to the target. See, far away from the target. Just one is close to the target. So I have a low accuracy and low precision because all the samples are different, right? And here, in the second student, look how precise this student is. all the measurements are pretty close to each other, but far away from the actual value. So I have low accuracy on this one. But I have a really bright student that has a very close measurements for each sample and very accurate because it's exactly very close to the actual value, the weight. Okay, so high accuracy and high precision. So the results of student A are both inaccurate, not close to the true value, and imprecise, not consistent with one another. Randall error is an error that has the equal probability of being too high or too low. The results of student B are precise, close to one another in value but inaccurate. Systematic error we have here is an error that tends toward being either too high or too low. The results of student C displays little systematic error or random error. They are both accurate and both precise, but it has small errors, right? And to solve the chemical problems, many of the problems you will solve in this course are unit conversion problems. You can convert meters to another unit. You can convert cubic centimeter to liters. You can convert moles to atoms. All about conversions. Units should always be included in your calculations. If you don't, you can get lost and also you lose points. They are multiplied, they are divided, and they are cancelled out like other algebraic quantity. So that we call dimensional analysis. A unit equation is a statement of two equivalent quantities. Like here, 2.54 centimeter is equal 1 inch. A conversion factor is a fractional quantity of a unit equation with the units we are converting from, or the bottom of the units are converting to on the top, like this case over here. So we have the unit that was given, and then I have the conversion factor. So then I will put the given unit down here so I can cancel out the unit, and I have the desired unit. This is how you use the conversion factor. In this case over here, imagine if I have 2 inches and I want to convert to centimeters. So the given that will be 2 inches. And then if I want to use this unit factor conversion, so I'm going to put an inch over here and then centimeter over here. So I can cancel out inch with the inch, and then I will multiply by this. And then we're going to have this 5.08 centimeter. Okay? This is how we use a factor, conversion factor. So a general problem solving would be identify the starting point, so the given information. Then we identify what you must find, like, okay, I want an inch. If I give it to you centimeter and I want an inch, or I give it to you inch and I want a centimeters, you need to read and find what they're asking for. Then devise a way to get from the start point to the end point using what is given as well as what you already know or can look up the conceptual plan. So let's go to an example which is better. The example that I gave it to you, and now let's go an example how important it is to write down the units all the time. Here, when you building conversion factors for units raised to a power, you need to remember to raise both number and units to the power. For example, if you want to convert from square inch and square centimeter, we need to construct the conversion factor as follows. 2.54 centimeter is equal 1 inch. So I know this, but how are we going to convert this to this? So you're going to square both numbers. So now I'm going to have this. So I know that 60.44 square centimeter is equal 1 inch square inch. So you need to work with the units. Otherwise, you're gonna make mistakes. Okay? If you have problems involve equations, you're gonna solve them same way. So you're gonna follow the steps. And another very important thing here is how to interpret the data. How you read the table, how you read a graphic. For example, here we have a table with mass of water and hydrogen and oxygen for 3 samples. When you look to this table, what you can see, what this table can tell you, because the tables need to talk to you as the graphics. So the sum of the mass of oxygen and hydrogen, I can see here, this plus this, or this plus this, or this plus this, will give this, the total of water in the sample. So it's the first thing that you can notice. We also can notice the ratio. If I do the ratio, it's 8 with a small variation due to experimental error. So you can do the ratio. Okay? So pay attention how you're going to interpret the tables and the graphic as well. For example, here, carbon dioxide is a greenhouse gas that has been rising as a result of the burning fossil fuels, such as gasoline or coal. So when I look to the graphic, you see like the different years, like 1900 compared to 1890, how increasing. And look at this point over here, it's increasing a lot, right? So when you look at this, right, the first thing that you could ask is why they'll go to 0? Why you don't have 0 over here? So we have 240, we start with because we started that with here 209. This is the data we have. So if I increase the graph until I get 0.0, so I will have a very great huge graphic, and the information that I need is stored in 290, which is the carbon dioxide concentration over there, right? So this is why. So that is why we don't begin with the 0 over there. So we see the rate is increasing, right? Represented by the slope of this line has intensified since 1960 until, look at this, 2020, how is higher. So the graph by itself must tells you and explain what's happening over here. A good thing here would be like the consumption of the fossil fuels close to this one to see if they're increasing the same ratio, right? So now you have a very strong foundation in matter, measurements, and scientific approach that completes the chapter 1. This idea, everything we do in chemistry moving forward. That's it. That's all. Bye for now.